welcome to the research introductions. My name is Kristine Nolan, and I am a professor in the Department of Chemistry with specific concentration in organic chemistry. So I'll be teaching organic classes, organic labs, and actually some inorganic classes as well. So today what I'd like to do is give you kind of an overview about what my group does, how we kind of fall into the big picture. And also I brought two of my research students here today, and they will give a little synopsis of kind of what they looked for in a group, how they joined a group, what did they learn being in a group. I actually don't know what they're going to say, so this will be an experience for me as well. So let's go ahead and get started. And if you have questions, please feel free to stop me. You don't have to wait to the end. You can feel free to interject as we go along, okay? All right, so in my research group, we kind of fall in the realm of what's called catalysis. And catalysis is a very interesting, vibrant field because it intercepts with a whole bunch of specialties. So we pull influences from organic chemistry, inorganic chemistry, physical chemistry, and biological chemistry. We kind of exist where all of these intersect, okay? So I'm going to get to what we do in a little bit more detail, but I want to first explain to you why we even need catalysis. You know, how does it fall into the big picture? All right, so let me ask you this. If I show you this slide, what do you guys see? What do you see?
Penguins.
I see a TV. What do you see?
Penguins.
You see penguins? Okay. So what these are examples of what's called an OLED. So it's an organic light-emitting diode. So you've probably heard of LEDs, right? So these are the newer generation, which are called organic LEDs. So there's actually organic materials in here that help to make the picture by emitting light. So when we as chemists look at these, we don't see penguins or blue boxes. We actually see the compounds that make up the polymers that emit the light, okay? So how about this? If I show you this picture, what do you see? Pills, spoon, okay? Well, once again, when we see this, that's not what we're seeing necessarily, but we're seeing what's inside of those pills, what's making up those pills, okay? And it can be as simple as this first structure, which is actually the structure of aspirin. Everybody's seen or heard of aspirin, right? They can get slightly more complicated when you get to something like this. And this is actually another one that you've probably heard of, which is cortisone. So this is for anti-inflammatory. They can get a little more complicated. This is what you probably know it as Lexapro, which is an antidepressant. And we can add even more complexity by getting to a molecule like this, which has the name of Taxol, which is an anti-cancer agent, okay? So I don't know how familiar you are with how we draw organic structures, but each of these lines means something. Where these lines intercept and we don't have an atom drawn, that's where we understand for a carbon to be, okay? So carbon's understood to be at the intersection of those two lines. And if we draw one line, that means something. If we draw two lines, that's telling us something. And also the shape of the lines, whether it be a wedge or a dash, is telling us something. So if you were to go into a lab and your job was to make Lexapro, one of the things you need to be able to do is to get the right atoms to be connected to the right atoms, or else you're not making Lexapro, you're making something else, okay? But not only do we have to worry about the right atoms being connected to the right atoms, but molecules aren't flat, okay? They're three-dimensional. So we not only have to worry about which atoms are connected, but where in three-dimensional space the atoms are connected to each other. So for example, this is cortisone. You'll see this oxygen-hydrogen coupling here, right? These two atoms next to each other. They have a dashed line that's connecting them. And what that tells us is that that atom, that oxygen atom, is actually back behind the plane of the screen. So in this three-dimensional representation, this little red dot right here that's kind of hiding, that's that oxygen. So you can see how it's actually back behind the screen. All right? Everybody good so far? Okay. So what if you get something like this? That takes a lot of work. There's a lot of bonds. There's a lot of things you have to worry about three-dimensional geometry. And you need a lot of tools to be able to put that together. Okay? So how do we control how to put some of those together? All right? So we need to think about that. What do we need to control if we want to make a molecule like that? So I mentioned two things. One, we need to control which atoms get connected. And we need to be able to control how they get connected in the right geometry. And the tool that we use in my lab is we use Catalysis and Catalyst, okay? So what we're doing is we're designing the tools that people can use to either use to make materials such as the OLEDs, or they can also use to make drugs such as Taxol. Okay, somebody has to make the tools that other people can use to put these things together. So how do catalysts work? Well, catalysts let us control these reactions. We can control the reactions by adjusting the activation energy. Who's heard about activation energy before, chemical reactions? Most people? All right, little refresher here. What does that mean? Well, in activation energy, going from reactants, so two things that are going to be coming together to make a product, there's an energy barrier to go over, okay? If there wasn't an energy barrier, then everything would just be reacting all the time, right? So you can think of this as if your starting material was this rock, and you want to get this rock to go to a lower energy level. Well, what you have to do is push this rock up and over the hill, right? The bigger this rock is, the higher the barrier is, the harder it is to get from starting material to product, right? So what catalysts do in order to allow that reaction to happen is we adjust the activation energy and we actually lower it. So without a catalyst, you have this big hill to get over. But in the presence of a catalyst, we can get a reaction to take place by making that just into a little hill. Okay, so as opposed to going over this big energy barrier, now we just have a little hill to go over. Does that make sense? Okay, so we will make a reaction happen faster by adding a catalyst. All right, so just to introduce you to what a catalyst is in case you're not aware, it is, as we've been saying, something that reduces the activation energy barrier, but it's a compound or a molecule or an atom or something even bigger like a protein that's not consumed over the course of the reaction. Okay, so it's used and regenerated, so you don't need to have a lot of it around, you just need a little bit. Okay, so what we just talked about was how do you get a specific reaction to take place. But you can also use catalysts to get selectivity in reactions to happen. So for example, this is a very simplified molecule here. A is connected to B. We want it to react with C. Okay? So C is floating around, has a choice. It can either react with A or it can react with B. Just two ends of the molecule. Okay? Very, very simple speaking. So in the absence of any catalyst, let's say that C has an equal opportunity to either bond to B or bond to A, and there's equal energy barriers getting to each, which means that you have a 50-50 chance of forming one product or the other, right? There's no way to discriminate between the two. But if we add a catalyst, what's going to happen? One of two things could happen. One is that we can increase the activation barrier going to one product, or we can actually decrease going to the other, or we can do both. If that happens, now you have a higher barrier going to one set of products versus going to the other set of products. Does that make sense? All right, so let's say you're down in this well, your starting materials, you have your rock. Which hill are you going to go over? You're going to go over the one to the left or the one to the right? Yeah, exactly. The one to the left, because it's the smaller hill. Okay? So what does that mean? That means that if you put a catalyst in with A and B and C, you're going to be forming the product where B is now joined to C and not the one where B is joined to A. So basically, this one disappears. Does that make sense? So that's how we can use catalysts to control a reaction. If there's two possible outcomes, we want one, we disfavor the other, and favor the one that we want. Pretty cool? All right. Well, this is not a new concept. Nature's been doing this for millions and millions of years. They have their own catalysts, which are called enzymes. Okay? So, for example, this is sucrase. And what sucrase does is it enables your body to break down sucrose. Okay? So you have sucrose floating in your body needs to break it down to glucose and fructose in order to be able to use it. Well, sucrose does not spontaneously do that. It needs a catalyst, or in this case an enzyme, which is a biological catalyst, to allow for that bond to break. Okay? So it binds to sucrose, it allows for a bond to break, the two components come off, and the catalyst is regenerated and go back through the cycle over and over again. Okay? It's pretty elegant. So your body's had long time to perfect these enzymes. And what we're trying to do is basically mimic this elegance in a flask. So this is kind of the perfection that we are always trying to obtain, okay? So in my group, we're using two different metal complexes to try to achieve some of these reactivity. Okay, the two complexes that we're using, one is based on a metal called rhenium, and the other one is on a metal called calcium, which we don't have a periodic table in here, so I brought one. Okay, and if you don't know where they are, rhenium is one of your transition metal complexes, right here in the middle. Okay, so these are your transition metal complexes right through the middle, and rhenium is right here. Calcium is one of your alkaline earth metals and can be found over here on the left. Okay, so those are the two types of complexes that we're using. And the reason why we're using them is one, they're key to the specific reactions that we're looking at, but also because they're pretty easy to handle. Rhenium oxo complexes, and these guys can attest to it, are what we call benchtop stable. You can make this, it can sit on your benchtop, it can be in a little vial, and it's not going anywhere. It's pretty rock solid, so it's easy to handle. Calcium 2 complexes, they don't like water, but they are readily abundant, they're environmentally benign, and they're pretty cheap. Okay. So what we're using is these metal complexes in the context of activating very strained ring systems. Okay, so for example, we are looking at this 3-membered ring that has an oxygen in there. So it's 2 carbons and an oxygen, that's called an epoxide. So what we're trying to do is make selective bonds to this epoxide and open it up. Okay? And we're also looking at the analogous 4-membered ring, so 3 carbons and an oxygen, that's called an oxetane. We're trying to open that up as well. Okay, and what some of the researchers in my lab have found is that in the presence of this rhenium oxo complexes, they've been able to do that to a certain extent. So we're starting to get this reactivity to happen. And they've been able to use these compounds here to open up these rings and selectively make the bonds that we've been looking for. Okay? In a related system, we're looking at a different strained ring system. In this case, this is what we call a cyclopropane. So it's 3 carbons in 1 ring. Okay, you can imagine there's a lot of strain in that ring. And what we're trying to do, once again, is make selective bonds to this ring and open it up. Okay, and what Justin's been able to find is that in the presence of calcium iodide, he's able to do that. He can open this ring up and make the selective bond he's looking for. Okay, these are in the early stages. We just started this summer, was our first summer. So we're starting to get some good reactivity, but it's really still at the beginning. All right, so why do research? Well, there's lots of reasons to do research. You want to learn something. You want to learn about some techniques. You want to answer some questions, gain experience, make some contacts, figure out what you'd like to do. Okay, there are people that are in the lab that have no intention to go to grad school, but you learn so many useful skills in the lab that you can take really wherever you go. But not only that, you're also there to have fun. Okay? So if you're not in the lab and you're not having fun, then find another lab to go to, because you really should be having fun and learning at the same time. Good? All right.